So this is a talk on unikernels. So does anybody know what a unikernel is who hasn't heard this before or heard me talk about this? Anybody? Excellent. Nobody has any idea what this is. This is great. So there's, I mean, honestly, you go back into the 40s, and we're learning about algorithms from the 60s and 70s. It's like if you go through all of what we do and try to find something that's new and interesting, it's really, really hard. And so if you're slightly cynical, and I'm not just slightly cynical, I'm massively cynical, everything that's cool and popular, I'm just like, whatever, man, this is, so I'm kind of a downer to hang out with and just ask, I'm just not that fun. I'm like, whatever, this has been around for 40 years. Who cares about this? So as it turns out, unikernels are another one of these things. Unikernels are, here's my, so I always say unicorn here, that's the reference, because it's bright. A unikernel needs an icon like that. So that's my unikernel icon. But a unikernel is really another throwback technology, and we're actually going way, way back to kind of almost the dawn of computing, maybe not the 40s, but kind of. So I want to go through that, but it's something that is very new, architecturally speaking. It does represent something that's fundamentally new, and I think important. So it's one of these weird things that I'm actually interested in. I'm not the standard of like what's interesting, but like I believe that this is important and interesting to learn about. So let's give it a try. Okay, I want to see that thing say 40. Can somebody hang on? I can do this. Yeah, hang on. No, my son. I asked my son. He's 10. We were having a problem with this. I said, Elliot, can you fix this thing? I gave him the requirements. I didn't write it up because like it's agile in our household. So we were just really like iterating. And so we were doing a jam session, and he like in 5 minutes he solved this thing, and I couldn't figure it. I mean, I'm saying that now, isn't that sad? I mean, it's cool, I'm proud of him, but why can't I figure this out? He figured it out for me. Okay. Unikernels are, I'll get into what a unikernel is, but this is really about a story about getting back to the hardware. I think if, we're programmers, and almost everybody here is going to be a programmer that engages in kind of our traditional stack. And I'll get into very specifically what our traditional stack is. And when I say stack here, I don't mean like, Mongo and Ruby. I mean like the full stack that goes all the way down to this thing. Oh, by the way, that's a server. You guys remember has anyone ever actually seen one of these things? That's a server, that's actual hardware. You have to put power in, and electrons, bzzz, they go around. It's real, it's like time and space. It all kind of comes down to that thing. All the stuff that we do, running in the cloud, through cloud APIs, multiple layers of abstractions, et cetera, looking for the very best website or web technology and frameworks, it all ultimately boils down to that thing. And unikernels are fundamentally about getting back to that thing. Okay, so what's a unikernel? Well, we're going to start with the hardware, and I'm going to build up just 2 layers. They're very, very simple. We start with the hardware, and then we layer on top of this a maybe hypervisor. And if you know functional programming, you know why I'm saying maybe. It's kind of a pattern, but I call that a maybe. That means it might exist or not. So it's 0 or 1. Maybe hypervisor, and then the unikernel. And this is like the full stack of software. So unikernel / unicorn, possibly hypervisor, and then your bare metal. I'm going to get into what a unikernel is right now. So a unikernel is this. It's essentially your operating system and your application all in one. All right, so I'll get into what an operating system is and all the layers of that, but you take that stuff, that layer, and you take your application and you make it one thing. That's a unikernel. It runs on, as we just saw, either bare metal or hypervisor. And it contains mostly, a good hypervisor contains only what is used. So you can kind of see here, in this interest of sort of getting back to the hardware, it's the minimalistic approach. It's going from a lot of stuff that we'll take a look at in a second to the bare minimum that you need to run. That's the premise. That's what the unikernel is all about. Okay, so, single process and address space. Is that important? Why did I leave that off? This is important. This is important. So I have to talk about this. So we're going to see that modern operating systems, when I say modern, it's very, very much in air quotes. It's modern, like this. Very much about running concurrently. A unikernel kind of turns that and says, you know, we're not actually interested in concurrency here. We're interested in really one single process that's running and one single address space. It's fundamental. It's a fundamental idea. Some unikernels deviate from that, but for the most part, that's kind of one of the principles. Okay. So here's a traditional multi-user operating system. By multi-user, I mean it's got like shell accounts. You can log into it. Like I'm going to sign in. You've got root. You got your account, somebody else's account. It's funny that we have that on our laptops. Isn't that funny? Multi-user operating system on our laptops. There's a reason for that. This is a traditional multi-user operating system. We're going to start with the hardware. There's our maybe hypervisor. We're going to add a kernel. I'm going to go back over this, but let me just zoom up to the top so we can see what this is. So there's a kernel, system libraries, the language runtime, application code, and configuration. So when I say stack, when I say like a traditional stack, I mean this. This is a stack, top to bottom. So going from, again, from bottom to up, starting with the kernel. The kernel's a thing that is the kernel. I'm going to use air quotes with that these days because the kernel is not really a kernel anymore. It's gotten real big, especially in Linux. Linux kernel is very, very large. But in principle, it's sort of the minimal thing that you need to run on in a particular environment. So it does basically, it takes the higher level system calls and translates them down through device drivers into sort of binary interfaces that actually operate on that hardware. That's the hardware level. And we have a maybe hypervisor, which is, I'll get into hypervisors in a little bit. On top of the OS kernel, we have system libraries. So these are sort of fundamental shared, what we'll call user space libraries that your application code uses. So lots of common system calls are provided at this layer called system libraries. Then you have your language runtime. So if you're a Ruby programmer, you have a Ruby runtime. If you're a Python programmer, you have a Python. If you're an Erlang programmer, you've got the Erlang runtime. That's the one, yeah. Okay, then on top of that, you got your application code. That's the stuff you write. That's the stuff that we actually write. I mean, this is the stuff we're interested in. This is all here. This is the stuff here that sits underneath that. And then configuration is another layer on top of that, which is also important. All right, contrast that back again to this. What's missing? Well, basically everything. It sort of compresses this entire stack into one thing. All right, you can almost think of this as like a real-time or an embedded operating system. But the tooling and the platforms, the software that's available for us to use is not really embedded. It's general purpose. And we'll talk about that. That's this maybe hypervisor layer. It's kind of getting back to sort of, let's write for the hardware. Let's be specific, let's target it, and let's not have all of this stuff if we don't need it. Right? That's the premise. Okay. So just to review here, traditional multi-user OS, originally designed for human-based terminal access. And you can get into the history of it, and this goes all the way back, actually not that far, to like the sort of mainframe, mid-frame, a little bit, Unix. Really Unix kind of introduced this to a large extent. But it's basically you got a computer and you want a bunch of humans to use it. And we still have these things on this. This is not an actual multi-user device. I mean, this is just for me. I don't have a bunch of shell accounts for people to use my laptop, but I still run this traditional multi-user OS on that thing. So do you. I think my phone is actually multi-user. Of course it is. It runs Linux. It arrived on desktops in the mid-90s. Of course, that's where it landed on desktops, so it was in servers before that. So it's used in the cloud. By the way, air quotes around cloud, I'm kind of a stickler for the old word called the internet. I'm just like throwback, I just think that was fine. We didn't have to call it the cloud. It seems to be a step backward. But anyway, we call it the cloud. Everything is the cloud. So I have a rule. It's an air quote rule. Whenever I use cloud, it's always that. So that's why that's quoted. Okay, so what about, why am I harping on this? Why am I outlining all of these things, all of this stack? It seems kind of bad that we have a multi-user operating system, maybe when we don't need to. That's what I'm getting at. So what's my deal here? Okay. So let me ask this. This is a question to the audience. What's a big application? How do you define big? What's a large application? Let's just pick lines of code. as a measure, is 1,000 lines of big application? Huh? No, it's not. It's definitely not. Is 10,000 lines of code a big application? It isn't. It's not. You're right. Is 100,000, this sounds like a joke, it's not. Is 100,000 lines of code, is that a big, is 100,000 lines of code a big application? Okay, good, you're starting to mumble. That's where it starts to, that sort of starts to get a little confusing, because it depends, right? It depends. 500,000, so here's how I kind of break this down. Small applications are clearly, in the thousands and tens of thousands. I would say medium to large applications are measured in the hundreds of thousands of lines of code. Really, really big applications, and these are things that you'd be writing over multiple years with teams, are in the millions of lines of code. Interestingly, before I get to that, did you ever see the Google presentation on their monolithic source code, where they have 2 billion lines of source code under management, under one repo? 2 billion with a B. You're laughing. No, it's true. I mean, well, I don't actually know if it's true, but why would they make that up? It's insane. That's insane. And of course, that covers all of their operating system, derivatives, and they have a lot of software, so it does make sense. But that's a lot of code. That's a lot of code. That's huge. That's beyond huge. That's Google. Okay, so. All right, so to give you an idea of the size of the Linux kernel, we have a graphic here. So in 2001, it was roughly about 4.7 million lines of code. That's a big application. That's a really, that's a sizable application, but it's an operating system, so you'd expect it to be pretty big. But that was a while ago. Recently, 2015, this was probably about a month ago, it was at 20.2 million lines of code. Big, big, big. That's a big app. And you can kind of see the trajectory, and there doesn't seem to be much signs of it slowing. There's lots of commits going on. There's lots of new features getting added to the kernel. Lots of modifications going on. But that's a big application. This is a graphic on the Debian distribution. So this is the source code of Debian. Now this includes the kernel, but it also includes literally everything else that ships with Debian. So it's all the user space libraries, all the applications. Okay, so we would go back here to the kernel, and it's about 20.2. I've shown the kernel over here in blue. You can't really see it. So it is small relative to the 778 million lines of code, which, by the way, is approaching 1 billion, right? That's right. If my math is right, 778, it's kind of getting out there, and it will get to 1 billion. There's the billion mark. It's getting there. That's Debian 8 as of 2015. So this is a really big, that's not an app. It's not one app, it's, it's thousands of apps, but it's a lot of code. This graphic shows the distribution of languages used in the Debian source. So basically, the language name, if it's used more, it's bigger, and the scale is accurate. So if you can see here in the middle, hiding, it's hard to see, but if you squint, you'll see that the largest component of all of Debian, including the kernel, is ANSI C. So that's C. Right? That's good old-fashioned C. Next, not a close second, but still very big, is over here. That's C. What's CPP? Because I've never heard. That's C++. All right. That's C++. So does anyone program in C and C++? How do you guys? Is it easy to spot bugs in those languages? Oh, in particular, this one. I mean, maybe this one, it's better. But this one, and I like to point out shell script over here. It's one of my favorite languages. But we've got Java, Python. This is basically as you'd expect. I don't think this is weird. That's weird. XML shouldn't be in there like that. I don't know. I should pull that out. I'm not sure how. If you're programming in XML, just talk to me afterward. I'm going to help you just reorient career-wise. I don't think you're doing the right thing. Yeah, it used to be. Cold Fusion, kind of an XML language. Okay, so Garrett, what's your point? Get your point here. OpenSSL has nearly 500,000 lines of code. It's used by over 2/3 of all web servers, and this happened. Does anyone know what this is? Did anybody, yeah, it's Heartbleed. It's you can see actually, quite literally, it's Heartbleed. You didn't know that, it's probably called Heartbleed, judging by the icon there. It's Heartbleed. Did anyone get a pager duty, or did anyone have like their whole company call them violently and say, hey, I think that we're in trouble right now? Anybody? I did. It was, I try as much as I can to ignore pagers. I just find it like humiliating to have to like respond. But this wasn't a pager. This was like everybody contacting me with like alarm. So I'm like, okay, this is probably real. And as it turns out, this was significantly real. This is a horrific vulnerability that affected most of the web. Oh, and by the way, that means most of civilization. So this particular vulnerability was quite serious. It basically allowed an attacker to get your secrets, to get your passwords, to impersonate you. And the attacker could do that as long as he or she wanted. Sit there and funneling off secrets. It was quite serious because of its widespread and because of its sort of straightforwardness in exploiting. So we had to patch that very aggressively. So here's the problem as I see it. Most software today relies on literally tens of millions of lines of code, most of which is written in C. And if you've written much C, you really you appreciate how easy it is to make a mistake. It's not even a mistake. Like it's not something, C is not like a moral, it's just like, it's like a sieve of problems and potential security vulnerabilities and memory leaks and overflow errors. It's difficult. And it's a credit to our civilization that we're able to use this language for so much, so effectively. But I have a question about that. I'll get to that. It's also shared universally. So we have this kind of inbreeding problem where we've got these libraries that are widespread throughout all of our code. They're inscrutable, but for a few people, literally a few people, for any given system library, you would be very lucky if 6 people were experts in that particular code. Usually it's 1 or 2. So it's inscrutable code, and it was written a long time ago. It's written before the age of hypervisors. So I want to shift over and talk about hypervisors for a little bit. But let me stop there for a second. What I'm talking about basically is we have a legacy of code that I think is kind of troubling. And I think hypervisors provide an interesting path to address what I think is a very serious problem. Okay, so what's a hypervisor? A hypervisor is something really simply that creates a virtual machine. I'll show you a couple examples in code of what that looks like. Naturally, as we've learned here, that they were invented in the 60s, everything was. Hypervisors can run on bare metal, or they can be hosted. And so there's different styles. These are generally the 2 high-level categories of hypervisors. Certainly the historical motivation for hypervisors was to exploit hardware, was to make it more utilized, because it's difficult to fully utilize hardware if your sort of level of granularity is a certain size. It's just difficult to fit a certain number of blocks onto a piece of hardware. And so hypervisors essentially allow you to make these blocks smaller. And it's a huge business in the early 2000s and continues just to utilize hardware. So hypervisors have come of age over the last 10 or 15 years and are completely ubiquitous, completely mainstream, and very, very good. So hypervisors today, if anyone's ever run an EC2 instance, they've run a hypervisor. You're running those instances. It's a virtual machine, so it's not an actual piece of hardware, and you're running it in a hypervisor, in this case Zen. If you've ever used Vagrant Up, you're running in a hypervisor. This will run VirtualBox or VMware under the covers, and you're going to instantiate a virtual machine, and you will run it in that hypervisor environment. So we're all used to these. They are completely ubiquitous. They're completely standard. They're off the shelf. They're affordable, and they work very, very well. So this advent of the hypervisor, really it's the affordable hypervisor. Cheap, good, performant hypervisors are enabling this Unikernel story. I'm going to follow up on that. So what we're really talking about here with hypervisors is an opportunity, with Unikernels, is an opportunity to sort of reevaluate the way we've been doing software. And if we go back in time, and we're looking at technology that's probably 20 to 25 years old, and it was built under certain assumptions, and it was built with a certain sort of historical context. And we're at a different historical point now. So I think we can look at all this stuff that we're using and be somewhat critical about it and say, you know, is there a point at which we can now take a step away in a completely clean and new direction? So I keep saying hypervisor, I mean unikernels here. Unikernels allow us to do that. So in the unikernel space, we're looking at a few different things here. People are now starting to get away from C. Like, you know, C is great at the machine level, but compilers, especially compilers of high-level languages, statically, strongly typed languages, can do some incredible things. And we probably don't actually need C anymore. I know it's going to be controversial. Somebody's going to leave the room. We don't need C anymore. I'm out of here. This is ridiculous. But I think most of us probably can get by, for the most part, without using C. But as you'll look at some of this technology, compilers are doing radically crazy things in terms of compiling down to native code, highly optimized code. Haskell. Let me look at Haskell. It's just a beautiful system for compiling down to performant binary code in an extremely high-level language in a functional sense. So we're looking at high-level languages here, modern type systems, modern compilers, and this all goes together to say, hey, we're going to now potentially look at a completely different model that is not tied to this heritage of C. So here's the opportunity as I see it. If you're looking at a greenfield application, I think this is in play. And again, I will get into some examples here. So I know you have a placeholder, like, okay, I understand unikernels are this attempt to get down to the hardware. What I'm saying here is this requires a break. And so to do a break, to go from A to B, a lot of times this is enabled through greenfield applications. So new things. I'm going to go build some new app. So I don't necessarily need all this stuff. So this is enabling some of these, some new application development here. Unikernels will encourage very small and focused applications that will remain small and focused. And I'm going to follow up on that with some architectural points at the end here. And we can finally look at security as a first-class citizen, meaning performance and machine compatibility are no longer the primary drivers in our work at this lower level. We can say security is going to be set forward as a first-class citizen, something that we must put first and foremost. So this is the culture, I think, of the unikernel space. They're looking for new applications, opportunities to build new things that break with the past, small and focused, and they highlight security as a prime directive. So, of course, when you tear down and just ignore the past and start over, you do so at a cost. And this is probably the biggest hurdle for anybody adopting unikernel technology. You throw something away, it is expensive to build it up. But this is the trade-off. And I think that for certain applications, this is a meaningful and acceptable trade-off. All right. So when you take a unikernel and compile it down to this thing, right? We said that the unikernel is the operating system plus your app all compressed into one. What's going on here is a smart compiler is taking all your code and eliminating dead code. Just take a second to think about that. If you can eliminate all dead code, and what I mean by dead code is code that's not used, never will be, never needed, it's not going to be there to exploit, it's not going to be there to attack. You reduce the attack surface of your application dramatically. You cut out literally tens upon tens upon tens of millions of lines of code because you don't need them. Right? So you can take all of that, I'm going to call it code bloat. That's what I think it is. It's bad. I mean, if you don't need it, it's going to just sitting there making your application vulnerable to attack. You can cut it all out. So unikernels give you the ability to do that. You can statically compile them. So what do I mean by this? You take this thing, you take your code that you wrote for your app, and you compile it down to one image that is not dynamically linked. So all of its dependencies, all of its code are sitting in one single file. Not only is that more reliable, but it's far, far more secure. It enables a completely new model of deployment and upgrades. You're no longer seamlessly upgrading shared libraries, but what you're doing is taking your code, you're throwing it away as one unit and replacing it with one unit. Now, you might not be in operations, you might not keep systems up. I've been doing it for a while, and I can tell you that model of application deployment is profoundly better in all ways to the ones that we're mostly using now. In terms of reliability and security, this promise here of a completely statically compiled image is profoundly changing in terms of the quality of code that we put in production. And this is a really interesting feature. So who here has heard about this immutable infrastructure? Yeah, it's one of those things, right? It's one of those popular things that, yeah, immutable infrastructure. Infrastructure is code. We're gonna put our configuration in code like that's like a breakthrough. So yeah, we're gonna define what we do systematically. Wow, that's amazing. This is really interesting. So there are some unikernel projects that are letting you build one of these unikernels that can actually be sealed. Once it's loaded, you cannot change the memory footprint. You cannot make modifications to the running server. Right? Because it's unikernel, you're running a server, you're running a virtual machine, it's sealed against change. That's actually immutable. That's effectively like an FPGA, you're burning something into a chip almost. I mean, and if it's broken, what do? You just throw it away and replace it with a new one. But I mean, in terms of like reliability and predictability and security, it is a complete game changer. So unikernels are sniffing around this, they're pushing down this path. So it is a radical step forward in terms of security. And very similarly, you have strict buffer overflow controls. I know everyone's been asking, you've been thinking in the back of your mind, yeah, security, 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 whatever, but does it scale? Is it performant? Are these unikernels something that I can drop in and make my application go 10 times faster? How many people here think that unikernels can help your application go 10 times faster than it goes today? How many people? Anybody? One? No one? It won't. It won't. Why? It doesn't make any sense. Application code is super optimized today. This has been our fixation. Our security problems are a result of our fixation with performance. So it's difficult to optimize. So what the unikernel space is doing today is it's trying to hold serve. So what you'll see is people making comparisons and saying it's just as fast. In some cases, it's much faster. But I don't personally think, there's going to be some people who disagree with me. But I don't care. I don't buy this performance thing. I'm not a big performance guy. I think it's largely an emotional, physiological drive that we have to be faster. So I'm not into this question. But for those of you, just to taste kind of some of the coolness here, don't do it now, but go, this will be online. So this thing Zerg, some, I don't know, like Klingon Star Trek thing, I don't know what it is, some Star Trek? Oh my, I'm so sorry, I didn't know that. Yeah, wow. Tough crowd. No, it's okay, we'll definitely watch the Zerg after this talk. So the Zerg, so I guess they're small. I know it because so they're small things or something, they swarm you or whatever. So zerg.erlang on zen.org, if you hit that site, you'll get a web page. That web page is served by a virtual machine that's dedicated to that request. And it takes about anywhere from 250 to 500, 700 milliseconds to serve, which is what most Ruby applications do on a good day. Yeah, no, so a whole machine, no, I'm just kidding. Ruby's awesome, no. So I know there's a lot of Ruby people here, so come on, just having a little bit of fun. So this is really interesting. I mean, they literally will spin up a virtual machine to serve your web request. And of course, you wouldn't do this. You could. I mean, you could kind of see sort of on-demand, lazily instantiated applications here, but that's maybe a little bit of a mental stretch. The point being that you can create a standalone virtual machine and instantiate it to where it's serving network requests in millisecond time. And I have seen reports of single to double-digit millisecond boots of virtual machines. So it sort of changes the game a little bit in terms of how you look at what a piece of software is and its level of isolation. So this is, in terms of like the whole scalability story, it's a bit of a twist because it has nothing to do with scale. It has more to do with, well, it is, it's performant. I mean, it's interesting to see how a virtual machine could potentially be spun up on demand and the types of applications that could come out of that. I don't care though, I really don't care. I really don't care about the speed thing. It just bothers me. Such a preoccupation with speed. I'm much more interested in security. Why? Well, who's seen this? Yeah? So I mean, So this is a show. This is a show. It's a TV series, and it's about a hacker. It's actually a bunch of hackers. It's about a bunch of weird stuff too. It's an interesting show, dark and messed up, making it awesome. But it's kind of scarily realistic, and like I was frightened by it. I don't know if you were, but I watched The Walking Dead and they're zombies. I'm like, I know that can't actually happen. It can't. I tell myself. They actually can't. I mean, I'm not afraid of them, but I was actually afraid of this show. I'm like, you know what? I could totally see that happening. And oh my gosh, like what do I even do? So I started to get a little bit alarmed. Now I don't mean to frighten anybody here, right? So I mean, I'm not going off on a limb and trying to like show imagery that is going to be terrifying or anything like that. But this is just a different movie. This is like another. That's my favorite movie, so that's why I have that up there. No, I mean, think about it though. I mean, we talk about water supply, we talk about electricity, the grid, we talk about other infrastructural components to our existence as human beings. But I mean, technology. We're talking about like driving cars, like cars driving us that don't have people. That actually sounds like a great thing, unless it's like this guy doing, or this guy who's like, programming my car to, ram into. I don't know. It's just this thing's. So the security, the security topic for me is, I don't want to be paranoid, but I really do think about, okay, forget today. Think about 20 years from now, or 50 years from now. We're essentially a bionic organism, right? Humankind is essentially interwoven. It's Gibsonian, right? It's already happening. You can see that. So security really does need to start becoming very, very important in what we're doing. And we have the technology to do it. I think that unikernels represent one path to explore in that area. So for me, the unikernel story really centers on security. Okay, so that's, there's nothing really super sexy about security. Well, I don't know. I buy that. I totally do. This guy is terrifying, especially if you know his backstory. It's messed up. All right. In addition to the security thing, I really think that there's some interesting architectural upside or potential that comes out of unikernels. So, how many Erlang people in here? There's a lot of Erlang DNA in the conference. It's good. Oh, it's good. It's good DNA. It's good DNA. So, if you write programs in Erlang, and I might throw Elixir in there because it can't help itself, but do these things, right? It just happened, Hey, Erlang is sort of predicated on writing really, really small things and staying very small. You can't write big things. It's impossible. And it's a function of its architecture. It's not because it's an extremely disciplined community. It is a disciplined community. But it's the architecture, it's the design of Erlang that results in the type of software that gets written. Things are small and focused and independent, and it is a beautiful, beautiful thing. And systems engineers ought to follow that. Indeed, Erlang was taken out of the systems engineering space. So its design principles reflect a lot of good design principles in engineering in general. So if you go down the unikernel path, you will get this. And I just know this restriction will result in new sort of application architectures that will be fundamentally better than the monolithic applications that we build today. I know it will. I've seen it. So this is extended not to a language, but to everybody. So if you just say, I'm going to build everything in a unikernel, it's going to force you to do some very interesting things. And those things, I believe, are very good. It's true. It's a black box design. You can distribute these things. This is all sort of off the back cover of the Erlang box. But it does apply. I'm not making it up. It's tolerant about it. Does it seem familiar to any Erlangers? So if you're into sort of the systems architectural thing, you just say, hey, every single line of code that I write from now on is going to be for a unikernel. You will single-handedly drive all of this. You have to. It will, and you'll write some pretty interesting applications. And I think that's where the industry is going to go. Yeah. So here's some possible applications. We've talked about small, but it really does need to be small and focused. I think possible applications today. Systems evolve, so you can have quote-unquote applications that are very, very complex, but they're systems. They're not really applications. What I'm talking about here is a traditional application. So I'm going to go build an app. And I'm going to take my compiler and write the thing and compile it and run it. So that's what I'm talking about. I'm not talking about systems. So you want to pick something that's very small and very, very focused. I think that the sort of analytics / compute engines are a complete no-brainer for this. So in other words, stateless. You're basically deploying algorithm or functional capability that needs to go run in a hypervisor someplace or on some sort of bare metal cluster. Very, very, very good application for unikernels. These are typically small and focused, and it's this type of thing that can boot in milliseconds to go serve different requests. And if you're hyper about security, you can seal them meaning you seal them off against change to ensure that they are in fact immutable applications. I think this is very good for routers, things that can spin up quickly and make decisions and route. And you can have very interesting networking, sort of networked-enabled topologies, systems using a unikernel. So if you have a router, I think that's a very good application for a unikernel today. And monitor, again, this is sort of like a security focus. If your goal is to write something that's very, very reliable and secure, why not try this? Right? It's small, it's focused, what do you have to lose? This is I think a good application. So monitoring and auditing, verification of correct behavior. I think that unikernels are a good potential fit there. So very quickly, because I want to have some time for questions, this is tough. I spent some time, I was really ambitious with this. I wanted to run this thing. I wanted to do all sorts of crazy things. I wanted unikernels draped around the theater here and shooting lasers and showing how amazing they were. And it's really actually, not only I didn't have the time, but this is actually pretty hard to get into today. It's gonna get easier, folks. Don't worry, it's just a little tough, I think, today. I mean, check back in a year or just make it happen. Just go in and do it, but it's a little bit tough. I think we are now sort of emerging from the proof of concept phase where it's like, okay, yeah, this actually works. We're actually able to do this stuff. So it's emerging from that. That's very exciting. So now it's like, okay, what sort of things can we do? What kind of applications can we build? So, and better platform support. So, can we run on this platform? The answer is increasingly yes. So this is an emergent field, but it's a very exciting time for unikernels. So of course, in time we'll get maturity. So that's, probably a lot of us are just waiting for this to get mature. But if you're a hobbyist or an early adopter, then this is something that's very cool to check out. So very quickly, we've got some of the bigger unikernel projects. This is sort of, in my opinion, the thought leader in the space. And I pull a lot of my understanding of what a unikernel is from the way they define unikernel. So this is an OCaml project, and the work these guys are doing is astounding. I mean astounding. I think in 10 years, we're going to be looking back at this project and saying, this was a pioneering work in computer science. Maybe I'm overreaching. I don't think I am, though. I think this is what they're doing is fantastic. And I'm using this to learn OCaml, so that's cool. Okay, so Ling, of course, it used to be called Zen on Erlang. It's called Ling now. I'm not sure where Ling comes from. Probably Star Trek. Ooh. No, is it? Is it? No, there's no Ling. That doesn't sound like a Star Trek thing. Zurg, definitely Star Trek. So we have. So this is a really cool project. It's running Erlang on Zen. So you've got the hypervisor field, but they're also getting it going on ARM, like bare metal. So low power, low compute processors. So these guys are doing some amazing work. So keep an eye on that project. If you're an Erlanger, that's a no-brainer. HALVM is a Haskell project. This is not really a unikernel project, but it's the best shot at migrating existing, especially POSIX applications, Java and POSIX applications. If you are interested in looking to move something into this sort of more isolated, more secure platform, this is definitely the place to look. There's some trade-offs to be had. They create larger images, but they are doing some pretty cool stuff. And then there's a bunch of other things which are kind of poke around the field, but aren't really unikernels. But we don't need to get in religious wars now. Wouldn't that be silly, right? So we look at these things and it's like, this is a good fit for what I want to do, then you use it. So don't worry about, oh, you're not a pure unikernel. Your image is like 5 megabytes. Ridiculous. Yeah. No, I do that. I would be like, You know, you see the bars, immediately you're like, oh, I don't want that one. No, no, yeah, that's the good one. Yeah, these guys have the smallest one, so I'm drawn to this, like the 100K. Yeah, that's a real Unikernel. Yeah, let's not do that. That's silly. Let's get 10 years at least, and then we get in religious wars, and then it'll be a blast because everything will be happy. Okay. So I would encourage you just to don't worry about it. Don't worry about like, oh, is it, you know, how's it going to go for my career? This will not help your career unless you're like, you know, heading up a group in your, you know, that has to nail security for some reason. And then I totally would do this. Absolutely, you need to do this. But, you know, if you're just learning programming, I would probably not. No. I'm going to back off of that. No, stop. If you're learning program, go right now, get Mirage, and learn OCaml. That's the way you learn programming. Right here, baby. So yeah, that's right. Or Erlang, or Haskell, any of these top three. I think you're fine. Okay. Wow. 1 minute and 17 seconds left for discussion. That's Unikernels. So thank you. Okay, so because I gave myself 1 minute, so let's one question, maybe two. You know, actually, you know, I don't have to talk myself off, so I can just stay up here all day, right? There's no one gonna.
Me?
Yeah, can you? We want to do a mic. Oh,
sorry. So obviously, container technologies wouldn't go far enough.
Oh
to
yeah,
take
Docker.
Things.
Oh yeah, thank you so for bringing Docker.
I didn't say Docker.
Oh, you didn't. Container technologies.
I said container technologies. But would you be okay with something like AWS Lambda for an analog for the concepts?
Yeah, totally. I mean, the same sort of architectural models come out of that. I mean, I mean, this is literally you're compiling an image that will go onto a machine here. So I mean, you can go and find like one of these little boards and run them, or your laptop or something else. So it's a little bit more hands-on, but for sure. Running isolated code, but containment is not a new idea, Docker. Sorry, folks who think it's a big revolution. I don't even think there's contain. Honestly, the containment is so minimal there. The Unikernel stuff is really, really contained. So I'm fine with that religious war right now. I'm fine with that. I don't think I really answered your question, but I mean, containment, I just, Pavlovian response, I became angry as soon as you said that. Yeah, I mean, if you hear container, it's just a really big, wide field, and this is pretty specific. So when you look at unikernels, it's going to be a specific technology, and there's no wiggle room there. It's going to be what it is, and okay. So anyone else? I'm in red. Oh, go ahead.
You have one? So are there specific application areas where unikernels wouldn't be appropriate? Like, would you write a database with the unikernel?
Well, I mean, I think what's appropriate, it would sort of be a matter of investment, and what are you going to get out of it? So if you had a very specific type of database, absolutely, it's certainly being done for sure. So you're going to see a lot of innovative and new applications being built simply because it's all greenfield. Really, for the most part, this is all greenfield. What's the limit on the type of application? Nothing at all, simply because in a system, when you build things that are very small and independent, you can literally do anything. We're systems. I know that with the complexity of this model scales to the extent that we have this conversation right now. So it scales a lot. So yeah, you can do anything. You can build robots, cyborgian robots with unikernels. I said that first. It's on tape. Okay, I don't want to go over because that would be incredibly self-indulgent. So I'm going to walk myself off. That's it. Thank you. Oh. We have a break now. One more question. One more question. Who wants a question? Who's got a question?
Is there any evidence about more security other than common sense? Like actual studies? Because the x86 platform is not really secure by design, and they have added stuff on top like TPC and other things to make it secure.
Yeah.
But it's been proven that you can break out of an hypervisor, and that's, for example, one of the reasons why OpenBSD has never wanted to implement one.
So here we have a scientist who's like,
And I'm not a
do you
scientist.
have, you're acting, you're being very responsible and you're saying, now look, do you have any actual data to substantiate this claim? And I circumstantially, of course, it's secure, it works, it's great. All right, so your point is absolutely right. So especially if you're running on a hypervisor, what's hypervisor running on? Linux, yeah, or an operating system, or one of those 1 billion lines of code stacks. So that's the real criticism, and I should have had that in there. That's a very, very fair point, and that's spot on. You're really only secure as that layer.
Sorry to clarify.
Yeah.
I'm not even talking about like Hypervisor that runs on Linux kernel. I'm talking about just a hardware platform that it's not really secure by design.
So whatever's sitting underneath the hypervisor is subject to exploit. I would just say all things equal, you're removing moving parts and you're moving lots of code. So that I think maybe that gets into the area of mathematics and calculus. I think I've proven that point just by saying that, right? Sean, help me out here. These guys are mathematicians. I was right? I'm right about that. All things equal, like less moving. There's got to be some sort of thing out there that I can leverage. The other thing is that moving away from C into higher level languages that are statically compiled gives us a much better lever, I think, for controlling what it is we generate. So I think it's a step. I think it's a radical step improvement, but I don't have a lot of data. I think what we're looking at is a trajectory here. And it's new, it's different, and I think with the focus on security, you're going to get a fundamentally different level of security. So I am hand-waving for sure. But I think circumstantially, I feel pretty good, especially with that Mad Max video, that picture there. Okay, so that is it. Please stretch your legs. This is Signal has sponsored our break. So thank you to Signal. And we'll see you in 20 minutes.